So let's go ahead and dive into some of our material for the day. And this is going to tie pretty heavily into last time. Remember, last time we were talking all about superposition, right? What happens when we have more than one wave? So here's what we've got. I want to start with two big things right here, right? Interference, we have already seen. What happens is that unlike particles or blocks or balls or anything else that would collide, they bounce off of each other or they combine or they do something, but certainly they react to each other. Waves do not do that. Waves do not care about other waves that are traveling nearby. And that means that the net effect on the string as we would see it is that these waves simply add together how much they're displacing the string or their medium or whatever they're going through. So in a case like this, what we would see is if those two waves were to line up perfectly, then we would get an even bigger wave. They would just add up together, right? And this is keeping in mind all of these things are currently, let's say that they are moving to the right. Everything is moving to the right. They're all just a bunch of traveling waves. In these cases, the wave would simply add up together. However, if they are off, if a peak lines up with a trough, then what we end up with is summing these two together, the wave disappears. And we call these two things either constructive interference, because they are building that displacement together, or destructive interference, where they have canceled each other out. So, how do we get these two different scenarios? And what do they look like mathematically? Well, there's a couple different ways that we can do this. Consider two waves that are nearly identical, traveling in plus x. Then if I was to look at the displacement of each individual wave, so let's say wave 1, wave 2, and each wave is going to have its own space, where it's at in space. Each wave is going to have its own phase constant. But omega t is the same. Because if we are going to have waves interfering, they need to be there at the same time. So t is the same between the two, but x and the phase constant are allowed to be different. Now remember here that phi is the total phase, not just the phase constant, but it's everything included here in the parentheses. So I've got my phase 1, I've got my phase 2. This interference will depend on the difference between these two phases, right? Where they are at in the wave. So for example, looking at something like this, let's go back to this picture. Hopefully it didn't look too far down quite yet. What is the phase constant of wave 2? What is the phase constant of wave 1? What do we think? Any guesses here? Any thoughts on these? What do we see for these two phase constants? I would think, if this is supposed to be based off of a sine wave, I'll say that my phase constant for wave 1 down here would be 0. Seems reasonable. Starts as a regular sine wave. The other one would be, we're exactly opposite of that. We are starting on the other side of the rotation. So my phase constant down here is pi. And this tells me a really important detail about what's going on with the destructive interference. Because when they are pi away from each other, they're exactly opposite. The entire way through, we get destructive interference. Now, what if? Let me get crazy here. What if instead of 0, what if it's 2 pi? Do you notice any difference? I shouldn't lean into that. I'm going to pull out those wires. Is there any difference between whether this phase constant was 0 and whether this phase constant was 2 pi? No. How can I tell? It's a continuous wave. I can't see that. For all I could care, it could be 16 pi. That doesn't make any difference. So I'm going to highlight this fact. Because this actual difference, factors of 2 pi, when you're talking about rotation, it doesn't matter. Because remember, when you go 2 pi all the way around, you're back to where you started. So when we see these things, when we combine all of these things, we see two different special cases. perfectly constructive interference or perfect destructive interference. And notice what's going on with these things. This is an m times 2 pi, where m can be any integer number. It doesn't matter which integer it is. Because what's the difference between 0 and 2 pi and 4 pi and 6 pi? There's not a difference. It's still just a rotation all the way around every single time. And if we rotate back to where we started, there was no difference in the first place. On the other hand, our destructive interference, exactly what we just saw. Now this is an m plus 1/2 times 2 pi. That means we are always going to get these odd quantities of pi. Pi, 3 pi, 5 pi, 7 pi, 9 pi. In all of those cases, though, it's a single pi. That difference means we have destructive interference. So now, there's a couple different ways that we can cause these things to be the way that they are. When we're actually going through and solving this, here's what we end up with. We take our phase difference, delta phi, and now I want to keep some definitions apart. We've got a phase difference, delta phi, at a particular spot. We also have the phase constant for each wave, that is the wave being generated from the source. And then we've got the total phase constant difference, so phi2 naught minus phi1 naught. And we also, if we want to get into it, it's just, there's so many different pieces. There's so many different pieces that we have to work with here. So what I might recommend for doing some of these problems, it might be helpful to actually go ahead and just have like kind of a block written down somewhere to say, okay, well, this phi is this phi is this phi is this, just to keep track of it all. Because I know there's a lot going on here. But let's take a look at what we've got. So if we are taking the difference between these two phases, phi2 minus phi1, I plug in what phi2 is equal to, I plug in what phi1 is equal to. Remember, it's the full thing in the parentheses here. And I get this, kx2 minus omega t plus phi2 naught, minus the other term. So again, the omega t's are the same, so those are going to cancel out. What's left over is this difference between the placement of, or how far the wave has traveled, and this difference between the initial phase constants of the waves. All in all, what we end up with here is what we see on the far right. K times delta x plus that difference between phase constants. So I can get a phase difference in one of two ways, or both. I can either have a difference in the initial phase of the waves, so that is the waves being generated from the source, or if these waves are traveling, I can put them at different starting points, and those differences of where they are being formed from in the first place will mean that we have a difference of path, and that can also create this interference. So here's our two big conditions that we talked about on the last slide, but blocked in, right? A little bit more clean, a little bit more of a stage for these two together. But we also notice that there's this equation down here at the bottom, and this is actually a pretty important one, I think. This is a really unique one because it tells us a lot of information. For partial interference, but this is not even necessarily one specific type of interference. This is any interference, because let's look at what happens. A brief revisit on this equation, because I didn't get it so well when I was in the lecture, and this is me coming back as an editor to finish this up just a little bit. My description for this equation was a little bit off, and I think that's mostly because I sometimes forget what absolute value signs mean. So let me describe this a little bit better. What we've got going on for any type of interference. Constructive, destructive, somewhere in between. It doesn't matter what type of interference we've got. Whatever it is, you get an effective wave created out of it with this amplitude. So anytime we've got something like that, what would actually plug into it? If we have some sort of interfering piece, then our D, call it int for interfered, would be essentially this A times just the rest of our traveling wave. Sine of a kx omega t plus phase constant. And it's going to be kind of an average of all those other values in between. So the x position will be like halfway in between each of these things, the phase constant halfway in between these things. All of these are essentially taking the middle route of each of these because each wave is contributing its own little tiny bit of this thing. So the actual interfered wave is actually split right down the middle with it. But what's actually going on here with this cosine in this case is what we're seeing here is it's 2 times a, and that is the amplitude of either individual wave, little a. We're assuming that they're the same wave. If the interference, if their amplitudes are not the same, then we have a little bit of a different equation, but similar things apply. But here's what we end up with. Cosine of delta phi over 2. The phase difference between my two different waves, divided by 2 though, because what's going on here is we're splitting the difference again between my two different waves. Think about what we can actually get out of this thing. If it's 0, perfect, right? Everything is completely in phase. And in a case like that, we have a maximized amplitude because we have our perfect construction case. In the other scenario, where we have some pi over 2, so that is to say the difference between them is pi, exactly what we saw here, a difference of pi, would land us cosine pi over 2, 0. That is our completely destroyed result. Anywhere in between, we just need to plug that in. And you might be looking at this and saying, okay, well, what about 2 pi? 2 pi divided by 2 is pi. Cosine of pi is not 1. And that's exactly where I got myself caught up. It's an absolute value sign in the outside. Amplitude is always a positive quantity. So if we see a negative 2a inside of this thing, because we had plugged in 2 pi or something like that, not to worry, take an absolute value. We always just consider the positive anyways. So, Edward and Anthony back out, back to the regular lecture. So, I want to try this out. Let's just kind of dive into this problem. And I'm going to recommend, try to do this 2 different ways. Try to do this first with a picture. Try to not dive into it too much with math. Try it with a picture first, and then try to with the math to make sure that both the results agree. But let's imagine 2 loudspeakers in a 20°C room. That tells us right there, we're dealing with regular room temperature, regular air, all of that good stuff. Speed of sound is 343 meters per second. There's a frequency, 686 hertz. Sound waves moving along the x-axis. Somebody is listening at x naught. If the speakers are in phase, we've got these 2 separate conditions, right? So kind of draw a split between these 2. It is not a part A, then part B. These are 2 separate columns. Keep them apart. Speakers are in phase in part A. Find what it takes to get perfect destructive interference. Speakers are out of phase. Part B. Find what it takes to get perfectly constructive interference. Take the next 4 or 5 minutes to work on this one a little bit and see what we can come up with. And then we're going to come back to this together and see what you got. All right, I think it's time we start taking a look at this. Actually, I want to check just a couple. There's some random things. I had to make some slight adjustments to sound and everything else earlier just because we're going to run into some issues when I try and do the demo. I already know about some of these issues ahead of time, so we'll see what we can do with them. See if we can mitigate them a little bit more this time around. Zoom doesn't like what we're doing. That's really the moral of the story in this one. But let's go ahead and draw this thing out. So here's what I'm imagining. I want to draw this thing. We know we're talking about stuff going on the x-axis, and I've got 2 different speakers and everything else like that, yada, yada, yada. But I'm going to start by drawing those 2 speakers, and I want to just do this thing with a picture to start. I want to try to get away from doing any sort of calculations or anything else like that. I want to start with a picture. So here's what I'm thinking. I've got 1 speaker, and let's make this a good-looking speaker. Yeah, look at that. Beautiful. Emitting a sine wave. Look at that beautiful sine wave, right? Perfect. Exactly what we need here. So here's what we've got. In part A, we know these speakers start perfectly in phase, right? That is to say their phase constant matches up. It lines up between the 2 of them. They're generating the sound at exactly the same rate. They're not necessarily at the same location, but the signals coming out of them time-wise are exactly the same. So that means we have a second speaker that looks like this. Now, we are tasked with these 2 speakers that start in phase where do we have to put them relative to each other so that there is perfectly destructive interference all the way over at our observer? Which basically means if it's destructive everywhere, then it's destructive of the observer too. How do we make these destructive? Right now, they're constructive. What if I do this? That looks pretty destructive to me. Peak with trough, peak with trough, peak with trough. Every single peak lines up with the trough. What's the separation between these two speakers? In phase pi, but that's not necessarily the distance. Remember, so the pi difference is the phase difference. To get that phase difference pi, that's what it means to have destructive interference in the first place. What I'm looking for is that 1/2 lambda, half of the wavelength. Because if we are exactly matching, then we have this perfectly constructive interference. If we go by a full wavelength, then we have what kind of actually lines up for once in a picture of mine. We have, again, constructive interference. Because we've gone from 0 all the way to 2 pi phase difference, a full wavelength. But if we only go half that distance, if we go half of the wavelength, then we line up with this perfectly destructive interference. So right off the bat, that tells us what our answer is supposed to be. Right? We're there. We've got that already. For part A, the phase difference between the speakers was 0, and we're looking at the picture. We can say the difference between the speakers' positions to make them perfectly destructive. So let me say the phase difference should be pi. That distance needs to be not 0.4 meters, lambda divided by 2. That's what I should be saying. Let me get back to some of these details. I'm thinking way too far ahead. Lambda divided by 2. So we have done most of the work already. The last little bit of detail we need to add here, we know that the speed of this wave is 343 meters per second. We know that the frequency of these waves are 686 hertz. That tells me right off the bat, V equal to F times lambda. Lambda must be equal to 0.5. So lambda over 2 must be equal to 0.25. Are you with me so far? Do we feel good about a response like that? That's how far we have to separate these two speakers to get perfectly destructive interference. And again, if we draw this thing out, that's moving this around like this. That's that difference between the two. That's what gives us perfectly destructive. So let's say you're working on paper here, and you have decided it's probably not within your best interest to draw out 2 identical drawings just like this, and take your scissors and cut one of them out and then try to overlap them to solve this out each time. Understandable, right? I'm not going to throw any shade at that. So how do we do this with equations rather than dealing with pictures like this? Well, here's what we need to think about. We know that the phase difference, if we want our destructive interference, our phase difference must be pi. Or better yet, it doesn't have to be pi necessarily. It's got a small variety of things it could be, right? It doesn't have to be pi. It could be 3 pi. It could be 5 pi. It could be 7 pi. As long as it is one of those odd factors of pi, we're set. Right? So here we've got this. This says destructive interference anytime we have this phase difference. Do it in red so it's really intense. Now, let's actually plug in what is the actual phase difference. How do we actually calculate the phase difference for many of these things? Well, I would take the phase of speaker 2 minus phase of speaker 1 and now we can start kind of canceling some of these details out, right? We know that the difference between these two phases is 0. That is to say, phi 2 naught cancels out with phi 1 naught, whatever that is. Omega t also cancels out. We're left with this kind of strange equation. Whoops, and that should be a 2 pi, shouldn't it? So this gives me a small variety of answers. Realistically, what I can do right here is I'm going to just replace this with delta x. That is to say, for the wavelength, or we're finding the wavelength, we've got the wavelength. We can plug in the wavelength here, and here's what we're going to find. M plus 1/2 times 2 pi is equal to 2 pi divided by my wavelength, delta x. Let me cancel out those 2 pi's. We don't need those there. The other thing that I can do is I can move lambda over. I can move m plus 1/2 over. Or actually, no, I'm solving out for delta x, so let's move the lambda over. Thinking about this wrong. The next problem's kind of similar to this one, so I keep getting myself turned around which one I'm thinking about. M plus 1/2 times lambda is equal to delta x. In this case right here, we asked for the smallest distance that would possibly give us this destructive interference. How do we make this as small as possible? Any guesses? What is m? M is any integer. Doesn't matter which one it is. Remember, all that's doing is saying, are we at pi? Are we at 3 pi? Are we at 5 pi? Are we at 7 pi? It doesn't matter which of those we're at. Right? The difference between those, if we go back to our speaker description here, really the only difference between them is something like this. Are we at negative pi? Are we at positive pi? Are we at positive 3 pi? Are we at positive 5 pi? Any of these that we're looking at, it's destructive interference regardless. M is allowed to be any number that it wants to be, and so to make it as small as possible, I'm going to say M is 0. Then delta x is 1/2 of lambda, which gives us the exact same result we found looking at the picture. So, part B, things have changed. Now in part B, one of our speakers is off. We are out of phase. And to be perfectly out of phase means that we are, again, our phase difference now becomes pi rather than 0. So our the difference between our phase constants is now some value of pi. And again, it can technically be any difference of pi. It could be pi or 3 pi or 5 pi or whatever it wants to be. At the end of the day, out of phase is out of phase because it's on the opposite side of the circle. If you have to go around 5 times first, it's still on the opposite side of the circle. But let me just simplify this and let's just call it pi for now. Now in this case, what is this actually going to look like on our picture? Well, and actually I should have drawn this not on this layer. Sorry, I'm trying to keep track of these layers to make it easier for me to kind of drag my pictures around. We know that the phase constant difference is equal to pi. We know we want constructive interference. Constructive interference means that the difference between phases is some factor 2 pi. So, what does that look like on our picture? Again, let's do the same method. Let's take the picture. Let's solve it out there. To start at pi means we're not starting here. It means we're starting here. So let's drag this thing over a little bit. combine with our new picture. That's what that thing should look like now. Now, if we take this whole thing and we try to line it up, how do we actually make this thing line up? How do we get constructive interference out of this? If we are completely lined up, we get destructive interference. Exactly what we saw last time. Same answer as before. Right? We have shifted our phase constant difference by pi, but we have also shifted our desired phase by pi. And in doing so, we're essentially just getting into the same scenario again. We need to be 0.25 away from each other. But let's run through the mathematics just in case. Here's what I'm thinking. I need this phase difference between the two. Let's get rid of this selection mask before I forget. I need this phase difference between the two to be some factor of 2 pi. Where does that come from? Two places. I'm going to just kind of skip to my result as I would see it over here. I get a k delta x plus my phase constant difference, which is not 0 this time around. So we get this, we get this, we get this. Okay. So now we're looking for a delta x again. Here's what I'm thinking. Let me subtract away that pi first. What do we end up with? M minus 1/2 times 2 pi. I'm subtracting pi over, so it's kind of convoluted here, but I want to bring that into the parenthesis. Because now, the reason that I did that is because now what I can do is I can say, okay, 2 pi divided by lambda delta x, cancel out the 2 pi's. We don't need both of those hanging around. That is to say, our very last step here is that delta x is equal m minus 1/2 times lambda. M is allowed to be any number that it wants. How do I make it the smallest number possible? Plug in 0 or plug in 1. Either way, it doesn't matter. I'm free to say that delta x could be plus or minus 0.25. Either way would work perfectly fine. And if we go back to our description, let's go back to our picture one more time. The difference between plus or minus is just this. Here's plus, oh geez, I want perfectly constructive. So here's plus, here's minus. Can we agree that either one gives me my constructive interference that I'm looking for? It doesn't matter which one I have taken, it is still the smallest distance between the two speakers. So I'm happy to see either plus or minus as the difference between their two spacings. Plus or minus 0.25. Let me even zoom out a little bit so you can actually see all this stuff. All right. So let's get plenty of good practice on this one, though. Let me switch back over to this. Let's try another one. Two loudspeakers emit sound waves along the x-axis, very similar to premise to what we just saw from here. A listener is at some point on the positive x-axis in front of both speakers. So again, very similar picture to what we just saw. She hears a maximum intensity when speaker 2 is at the origin, x is equal to 0, and speaker 1 is at x is equal to 0.5. If speaker 1 is slowly moved forward, the sound intensity first decreases, and then increases and maximizes again at 0.9 meters. What is the frequency of the sound? What is the phase difference between these two speakers? take a similar approach. There's a good way to solve this with a picture, although it's a little bit more complicated this time around. But if we see this, and then try it with math, we should be able to get some green answers. So I want you to take the next 4 or 5 minutes to try it yourself, and then we will come back together and see what you got. Just used the 343 meters per second, yeah. And that's, again, anytime we're talking about random, kind of, this time it was specified, but on average, just take 343, unless specified otherwise. Okay, I think I want to start taking a look here. So, we want to start with a picture again, because that's going to lead us to the most success, I think, as we're looking at this. This time it's going to look a little bit different, though, because I'm not necessarily going to draw the speakers in the exact same way like I did the first time. Instead, here's what I'm thinking. Let's start by drawing the axes, because that's a good thing to have, just in case. So, one speaker is located, didn't mean to do that, right here. And let's just, it doesn't really matter what it's doing. Let's imagine that it's emitting a sine wave, kind of like this. That is not a very even sine wave. Let me try that one more time. I don't know if that'll be better or worse. We'll find out in a minute here. So what we're going to do is we're going to snag this thing. And one of these is sitting right at the origin. Whoops, I didn't mean to do that. Try that again. There we go. One of these is sitting at the origin. But here's another interesting point that I've got going on here, is that the other one of these, this interference, we hear a maximized volume. A maximized volume suggests to me constructive interference. If it was destructive interference, then we'd hear nothing at all. Constructive interference means we hear the highest volume we possibly could. So then, I don't know what speaker 2 is doing, right? That's a little bit of an issue, but I do know that this wave down here lines up perfectly. So, and let's take a minute to think about what that just means, because really what we're looking at then is that there is some sort of mystery going on. Whatever's going on right here, I don't know what this looks like. I don't know what the wave looks like coming out of the speaker. I don't know what's going on in between these two. I do know, though, that at least at this point right here, these two waves should line up exactly. And now this distance that we've got here, x1, is the distance between these two. This is not a constant value. But here's what we've got. At x1 equal to 0.5, what do we know? We have constructive interference. That means the difference between the two phases must be some factor of 2 pi. The same must be true when x1 is equal to 0.9. It's not necessarily the same factor because, again, m can be anything. N can be 1, 2, 3, 4, 5, negative 10, whatever it wants to be. As long as it's an integer, it's fine. But we do know that we get constructive interference at both of these places. So let me just kind of highlight this to say constructive. Constructive, right? That's really what we're going for here. That's the numerical way to write down that it's constructive interference. But let's think about what all this means for a second. As we are looking at this piece right here, what we did was we took this thing from where it was before, and we said constructive interference. Then we got lower in volume, lower in volume, lower in volume, lowest volume, increasing, 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 maximized again. How far did we move? Distance-wise and wave-wise. How far did we move? We moved one wavelength. That's exactly it. We moved one wavelength. Now, what about the condition? Let me imagine a scenario real fast. So let me move that back to where it was from before. Let's imagine the scenario. If we didn't have this picture, if we only had these conditions, that we see constructive interference at 0.5 and we see constructive interference at 0.9, it could be true that the wavelength is only 0.2 meters. And why would that be? Because what we would have seen... I'm really bad at drawing sine waves. We need something like this and something like this. It could have been that we would have seen constructive interference here, constructive interference over there. But the difference is that had the wavelength actually been 1/2 of what we have just been asking for, let me try and do it on this one. I'm really bad at drawing waves. Something like this. That's all right. That could be a lot worse. If we had this and we had moved this exact same shape. Let me overlay it kind of a little bit above right here so we can look at this a little bit more clearly. And let me go back to this one and take my shape from here. If we had gone through and we had traveled the same 0.9, can we all agree we have constructive interference again? From 0.5 to 0.9, same constructive interference. The difference is that we would have heard another peak directly in the middle if it was another wavelength. We specifically heard started at max volume, went all the way down, went all the way back up. That is, we heard the next one in the sequence. This was the first time we heard this. It's not 0.2. We didn't hear peak, another peak. We heard peak, decrease in volume to peak. So we know the wavelength must be 0.4 meters. So now I need to figure out how I can actually get rid of all these things. I think it's just that one. Yeah. So we go with that information. We go with that information now. Now that we know that the wavelength is 0.4 meters, we can say, all right, now if we need to, we can solve out for the frequency using the exact same equation that we had just seen from before. That is, V is equal to the frequency times the wavelength. Wavelength is 0.4. Speed is 343. Frequency should be 857.5. Now again, fantastic way using the picture. I think it makes the most sense. It's easiest to understand. But we could have done this in the exact same way using equations. But I'm going to rely pretty heavily on my picture again anyways. What do I mean by all that stuff? Well, we could have said, all right, well, the phase constant, or the phase, not the phase constant, the phase difference between these two sounds has to be some factor of 2 pi. Must equal. So I would take my phase of 2 minus my phase of 1. Kx2. X2 is at 0. Omega t's are going to cancel out. What I'm left with is this. Negative Kx1 plus delta phi naught. Now, we don't know what this mystery is. And that makes it a little bit more difficult, and we're going to kind of get into this in a minute here. But what I can do is I can take this thing and I can say, okay, well, I've got 2 separate conditions here. Right, really, it's not just one thing. I have been solving this thing out with just x1, but x1 is 2 different things. I know this is true at 2 different locations. So here's what I'm going to do. I'm going to split this up into 2 separate equations. I'm going to split this up and I'm going to say, okay, well, whatever was going on at the 0.5, I'm just going to call this m of 5. and you'll see why in a second here, negative k times 0.5 plus delta phi naught. I'm also going to do the exact same thing with m now at 9, or m sub 9 is really what these are. I've got these two separate equations. M can be any number. It can be any integer. It doesn't matter what it is. However, we know some specific relationship about these two right here. And how do we know that? Because let's go back to our picture and talk about what we had seen from before. When we were looking at this thing, we said specifically that if we are looking at, I am not sure which of my layers is actually the one I want anymore, we're just going to combine these and find one of them. I have lost track of which one I'm working on. Let me take my speaker. We said maximum volume, nothing, 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 maximum volume. Or I mean, things happened, but we don't care about those spots. Nothing, no maximum volume happened between here and here. If m is any number, then what that tells me is that the difference between m at 0.5 meters and m at 0.9 meters was only one rotation through. They are one wavelength away, one complete oscillation difference. And I'm going to use that fact, put that back to its original spot here. I'm going to use that fact to say then, oh, still on selected layer. I'm going to use that fact to say M5 plus one more oscillation is equal to M9. Whatever they were. Whatever M5 actually was, it doesn't matter what it is. I know that 9 was one more than that. So now I subtract these two. And this has been a wonderful thing for me because now by subtracting these two, I have eliminated this uncertainty that I've got about this phase constant difference between the two. See, now I can get rid of these terms and I don't have to worry about it anymore. Now what I'm left with is I know that M5 minus M9 should be equal to -1. I'm left with a -2 pi is equal to, now this is going to be k times 0.4. All that's left. Now, I've got a minus sign here, which is a little bit troubling. And I think I might have messed up somewhere with a minus sign in one place or another. But that's all right. It's not actually that big of a deal for us. When we go through plugging in these numbers, what we still find at the end of the day, yeah, I feel like I certainly did. Where did I mess up a minus sign? Who knows? Who knows? I think I did something wonky with it. That's all right. I'm not super worried about it because what I'm finding here is that the wavelength is equal to -0.4, but the wavelength being equal to -0.4 is meaningless. What's a minus sign between friends? The wavelength should be 0.4. I think I messed up a minus sign somewhere, but I'm not entirely sure where. But if you find a minus sign in your wavelength, it's not a big deal. Just say, hey, whatever I did with my 2 pi's, whichever ones of these I've shifted, maybe I picked the wrong M. Whatever I did with any of those values, it doesn't actually matter. I know wavelength is always a positive value. So, picture, I think, is a much shorter way, but we've got to have good drawing skills and we've got to have a really heavy conceptual understanding of what's going on. For the very quick question, that is the very quick question as we will see it in the slides. We're getting there. So the last thing that we need to do here, we need to find the actual phase difference, delta phi naught. Here's what I'm going to do. I'm going to say, what's the easiest approach that I've got to actually get there? So here's what I'm going to do. It doesn't matter which one of these I really take. Not super concerned either way. I'm just going to take one of these things. Why am I still... Okay, there we go. Take one of these things. I'm just going to say m times 2 pi. It doesn't really matter which one I've got. Call it 0. Just make it easy. Call it 0. What do we end up with here? This 2 pi over lambda times 0.5. Negative sign. This is going to be equal. 0.5 cancels out with a 2. Pi divided by lambda. Lambda is equal to 0.4. This is a 2.5 pi phase difference. Is that any difference than a phase difference of 0.5 pi? Is there any noticeable difference between those two answers? Does it have any impact if we had used 0.5 instead of 2.5 pi on any part of this entire problem? Or 4.5 pi? Or 6.5 pi? For any phase-related value, you're pretty much free to add and subtract 2 pi anytime you want. It's not actually a big deal. Now, some of you are going to go into more in-depth wave optics one day, and you're going to remember that, and you're going to hate me for it. But for right now, it's totally fine. For right now, for getting through the rest of the semester and for getting through this material, you are welcome to add or subtract a 2 pi anywhere that you see phase. It shouldn't make any difference because it's just moving you back to the same spot through one complete oscillation. How do we feel about this, though? Feeling all right? Okay. So, let me try and blast through some of these details. And by blast through, we'll have plenty of time, not to worry. But I do want to get to this demo because I think it is really, really cool. So, let me move up here. What about when our waves are in 2D? No change. No change at all. Really. When we look at these equations right here, a phase difference of any factor of 2 pi is still constructive interference. A phase difference of any odd pi, 3 pi, 5 pi, any of those, still destructive interference. The big difference between the two is that it's a delta R instead of a delta X. Does that mean anything meaningful, though? No. It's no different. It's just your distance away from the source. We could have been doing this for both of our last problems, and we would not have noticed any difference because we're focused along the x-axis. Now it just asks, what if you're not looking along the x-axis? Now it's just R instead of X. And you guys know how to do Pythagorean theorem to find R at this point. I feel confident in that. There is no other difference between these two. Same deals for 3D. If I go to 3D, it's still even a delta R. We don't even change the symbol at that point, right? X, Y, and Z. You find the hypotenuse of that crazy triangle, and you've got your distance away. And the phase constant and all of that is settled. How we draw it is a little bit different, though, right? Because now we're kind of taking this top-down view. So I do want to kind of point this out. These wave fronts, as we're calling them, what these really are, this is the peak. This is the peak of the wave. So this is another peak, and this is another peak. That means that in between, we have our trough. And if English is not your first language, and even if English is your first language, I'm sorry about the spelling of this word. it doesn't look like that's right. I've looked this up multiple times to be sure. That is how you spell trough, but I've got some issues with that. English, we need to talk. But this is a trough, and this is a trough. Anywhere you see in the middle, in between the two peaks, you know it's a sine wave, so you know in between the two peaks is going to be a trough, a valley. So, I'm going to run this one kind of by example here. But let's imagine this. I'm going to do this first with just the picture. Point P. Is this constructive or destructive interference right here? Point P, what do we think? Constructive. Peak lines up with peak. That sounds like constructive interference to me. What about point Q? Constructive, destructive, or somewhere in between? This one is not a partial. Remember here that in between the peaks is where we see the trough. So this is a peak lining up exactly with the trough. This is destructive. Going along that same vein, what about point R? Constructive, destructive. Let me get to that in just a second. Constructive. Trough lines up with trough. Each of these, how do we know it's constructive, destructive? We're looking at the picture and we're saying, okay, well, if it's constructive, it's going to be adding up. Peak lines up with peak. That means perfectly constructive. In a two-dimensional wave, it gets a little bit more wonky, right? Because where we see the peaks and where we see the troughs, they don't line up as well as they do in 1D waves. The equation that we see to describe these comes out to be exactly the same. But the pattern that they take, it's not necessarily perfectly constructive or perfectly destructive for all of space anymore. There are certain regions where it is perfectly constructive, right? If we're looking at all of these spots right here, for example, I've got two sources and there are these tiny little black dots in the middle. What I'm seeing here is this is constructive, this is constructive, this is constructive, this is constructive. In between those, you see these green spots, the zeros, that's where it's canceling out. So this is destructive interference, this is destructive, this is destructive. What you get is essentially a pattern of constructive and destructive. Two-dimensional waves or three-dimensional waves as well do not just fall as cleanly into these pockets because they're expanding outward, right? They're not just going along down a line the entire time. So that means they create these patterns of constructive and destructive together all at once. And in fact, we can even move this picture. I've got another one of these things. You can see kind of where this is going along the lines here. The lines of constructive and destructive interference. So that's how we're looking at this and we're saying I see at point P, two peaks are lining up, constructive interference. And the way that we can prove this as well, look at these things. Are they in phase or out of phase? I don't have an equation for this. I just see they're kind of putting them out at the exact same time, and right now it looks like they're about to have another one. They look to be in phase to me. If they're in phase, R is constructive as well, yes. Then at point P, the only difference, if we're going back to this equation, 2 pi over lambda times delta R plus that phase constant. Phase constant in our case is 0, the phase constant difference. So that says that the only difference of phase that we would see is because of a difference of path. 2 pi over lambda times delta R. Well, what is R1? Or, yeah, what is R1? 1, 2, 3. 3 lambda. What is R2? 1, 2, 3, 4. 4 lambda. Delta R is equal to lambda. Lambda cancels out with lambda. The phase difference is 2 pi. We have constructive interference. Now, let's mathematically prove that Q follows into the similar vein here. If I'm looking at Q, here's what I've got. Phase difference is going to be because, of course, again, 2 pi divided by lambda times delta R. I need to find these two R's, though. R1 is 1, 2, 3.5. Okay. 3.5 lambda. R2 is 1, 2. So my difference of path, delta R, is negative 1.5. Negative 1.5 lambda, specifically. Negative 1.5 times 2 pi means our phase difference is negative 3 pi. Negative 3 pi, any odd value of pi, 3 pi, 5 pi, 7 pi, negatives included, that's destructive interference. Do we vibe all right with that? All right. So, and kind of like I was saying, it's just we get creative patterns with these things because they're all over the place. They're very strange. They're moving around all over the place like this. So the constructive versus destructive is no longer like an entire thing. It's localized areas that we see this happening. Now, all of these have been assuming that we have had two identical waves traveling at the same time. What about when I stop having them be exactly identical? If the waves aren't exactly the same, we run into this interesting situation where we, again, are essentially solving out. When we solve out, we add up these two displacements together. Our result is now this wacky thing. That is 2a cosine of omega modulation, t, times sine of average wavelength, t. And this is kind of meaningless on its own. The average is literally just average, split the difference between the two frequencies. Modulation is like a half difference kind of deal, though. So what is this? Well, it's easier to show as a picture. If I have two almost identical but ever so slightly different waves, then I get an interference pattern that looks like this. And notice, so our short wavelengths, that's the average wavelength between the two. That is our omega average, or our frequency average. But then we see this much larger scale pattern, and that's the frequency of the beating between the two frequencies. There's a running joke that maybe you guys have heard before. How do you tune two piccolos? Does anybody know this one? The answer, generally, is you kill one. You never have two piccolos. The reason being, two very high frequency instruments, if they are ever so slightly different in their pitch, you immediately get a very large beating frequency. And that pops up as a third frequency that you can immediately hear. You immediately notice this kind of modulation. You'll hear this sound. So, try this real fast. Really fast, I mean. You hear 2 beats per second when two sound sources both at rest are playing simultaneously. You've got two separate speakers. One of them is at 500 hertz, and you hear a beat of 2 hertz. The frequency of source 1 is 500 hertz. If source 2 starts moving toward you, and the beats disappear, what is the frequency of source 2? Okay, so let me walk through what I'm thinking with this. Two sound sources, both at rest. I've got two speakers in front of me, one going at 500 hertz, but I hear a beating frequency of 2 hertz. 2 beats per second. That tells me right off the bat the difference between 500 and my second source is 2 hertz. I've isolated down. My answer is either going to be 498 or 502. What happens in the Doppler shift when a source starts moving towards you? When the source starts moving towards you, the pitch shifts upwards. So if it was 502, I'm not going to complete that circle. If it was 502 and it moved towards us, it would start sounding even higher. We would get a faster beat frequency. But because it's moving towards us and it disappears, we know it has to be 498. The pitch shifts upwards, the two frequencies match, we don't hear the beating anymore. So, I've got some fun things going on here. And the first thing that I want to do, let me switch this over. I've got some demos for you guys. Let me switch over to this one, and let me show you kind of what I've got going on before anything else, because I have to imagine the very first question that you guys are going to ask as soon as you start to see this is, what the hell are you doing? So, first of all, we have this fun little setup right here. I've got my oscilloscope. It's attached to a few different things. You'll notice here that I've got, here's my signal wire coming in. The signal wire is connected by a paper clip to the ground, and then I've got this red wire connecting the signal, just an open wire shoved into the socket. On the other end of this thing, what I've got is half of an audio cable. I have split that off, I've wrapped another paper clip around that thing, and then done the exact same kind of deal of taking a copper wire, wrapping it around the middle post, and then shoving that into the slot. These are not typical connections that you would see to an oscilloscope. So we've had to take some extreme measures, and every single year I tell myself that I'm going to make a professional conversion box, and every single year I decide it's significantly more fun to hook it up with paper clips. So, it's perfectly safe. I can touch all these things just fine. No big deal. Right? None of these things are high enough voltage for me to ever even begin to worry about. So I want to start with this. Let me switch back to my other view. And what I've got going on here is I have this wonderful website that will generate all sorts of tones for me, anything that I want. And what I'm going to start with here is actually going to be this, not that E, that's a little bit too low, but I'm going to start with this E right here. And you guys may or may not be able to hear this. We're going to see what works. But here's what I've got. It's a low hum, if you can hear it. Try and turn up my lows a little bit so you can hear that just a little bit better if you can. It might be too low to see, but notice what we've got going on here. So this is at 82.4 hertz, and what we see on the screen here is about 3 peaks. Now, let me double the frequency. 6 peaks. For anyone that's musically inclined, what did you just hear? Octaves. That's the difference between separate octaves. It's always a doubling of frequency. So, what I keep doing with this is I keep shifting these between all of the different E's. If you wanted to look at this on a piano, every single different E on the piano, I'm going through some of those things. And I don't know how well you can hear this, but right now I'm set on 82.4 hertz. But these are all sine waves. So, what else can we do with this? Let's try and dive into this a little bit more. Let me bust out something that's a little bit more unique than just a sine wave. Right? This is going back to a little bit more of what we were talking about last time, about what can exist on a string, the standing waves. And somewhere, within all of this stuff, I've got cables that are just kind of mostly floating around. Again, things that are all very, very safe, I promise. It's actually not that spooky or anything else. That's why I'm very comfortable doing this. Usually I'm a little bit more spooked than other people when it comes to electronic safety. High voltage stuff scares me a little bit, but so let me switch this on. So that frequency that you're seeing right there is E. Whether or not you can hear it, we're kind of working with what we got right now. But let me stop that. Let me take this from the guitar instead. Ooh, that's a little bit loud. So it decays down because that's reality for most waves. But what do we see? I see 3 big peaks. Let me go back to the sine wave. 3 big peaks. Okay, so that's the same. But why do I see these extra little peaks on the inside? Does anyone have a guess? What are those? Why do I see a strange shape that's not just a sine wave? It is supposed to be a standing wave, isn't it? What do we see there? What I can tell you is that we're seeing all of the conditions that can exist on this string. See, remember, when we're talking about something like the standing wave, the string is a boundary. It says this end has to be 0, this end has to be 0. Any sine wave that can exist on that is allowed to. So what I'm doing here is I'm seeing not only the main frequency, but I'm also seeing the second harmonic. And somewhere in there is also going to be the third harmonic, and the fourth harmonic, and the fifth, and the sixth, and all of those things together. This wave is the superposition of all of those different waves at once. And this is actually a pretty close representation of what's actually going on the string. The string is making shapes like this, and they're constantly flashing back and forth. And I can essentially generate more harmonics, or I can put more energy into those harmonics by plucking in different places. So you'll notice that there's a little bit of a higher tinny sound to that. And again, you see it in the waveform. What's going on is that I'm putting a lot more energy into those higher harmonics than if I'm putting them into the 2 main ones. So let me talk about one more thing here. One other thing that we can do that's quite a bit of fun. We don't need this necessarily. But what happens if we begin to add more boundary conditions? We said, okay, 1 into the string, 2 into the string. We said, all right, well, those both have to be 0. Can we do anything else with this, though? We have to say this one is 0, this one is 0. Let me introduce another condition. Let me introduce this as a 0. Now what do we expect to see? So it's very much, again, like that octave up, which makes sense, because I would expect to see the second harmonic. But if you notice, and let me get a little bit closer so we can see this better, it still has that weird thing going on. It still has like this extra little peak. Why does it have that? Aren't I focused on the second harmonic here? What could that be? Any guesses? It's a lot to do with the fact that I'm trying to focus in on the second harmonic. And that is, of course, the first thing that we imagine to see. We imagine to see that we're going to see something like this. But the string doesn't care about which harmonic it's buzzing in. The string will buzz every harmonic that can fit under these conditions. So not only do I see the second harmonic, but I also see the fourth. And that is that extra little bit of a wave that we're beginning to see on the left side of each of these peaks. And why we see that strange pattern begin to emerge. Now, of course, that's not it, because there's also the 6th and the 8th and the 10th and every even harmonic all stacked together at once. It's just much in the same way. If I pluck it in different places, I put a little bit more energy into those particular harmonics. And that's a lot of what an instrument's timbre is, and how you can get different sounds from the same instrument, even if you're playing different notes. It's all about the superposition of all of these different waves acting at the same time that produces everything's unique sound. So that's a lot of the stuff that you can do on a string. And then, of course, kind of going back to the scene, all of these differences in the waves and hearing all of those differences between them. And we can keep taking this up if we really want to. We can begin to go into like this third harmonic, which again is going to be a stack of the third, the sixth, the ninth. I can pluck in different places and I get different harmonics. I can get the fourth, the eighth, the 12th, and so on. You can get all sorts of crazy sounds out of it. One of the other cool things with this, and this is kind of more along the lines of beating, I can take one of the most basic chords that is out there in music. It's called a power chord on guitar, but what it is it's two notes that line up with their frequencies very well. It's a 3-to-2 ratio. And that means that the pattern that is generated between the two looks kind of clean. Now, if I take something that's a little bit more grindy, you can see that. This is called a tritone. It's supposed to be a very, very dissonant sounding kind of interval. And perhaps an even more dissonant sounding interval is the minor second, and this one sounds really grindy. But you can see what's going on with those waves. The waves are just freaking out. They're going all over the place. There's a lot of strange interference going on between them. And that kind of sounds more displeasing to the ear versus two notes that are much more similar. And then, of course, getting into chords and everything else is a little bit crazier than that. The more rich sounds have more things going on in the waveform, but there's more going on. There's a lot more room for things to sound dissonant or to sound strange. Now, one other thing that I did want to talk about on this one is not just anything to do with the guitar. Let me go back to this. Let me go back to our frequencies one more time here, and here's what we're going to do. I'm going to take 82.4 hertz and play that, and if you can hear that, fantastic. If not, not a big deal quite yet. And I'm going to go to not this, but I want to have 83. I don't know if you can hear this, but perhaps you can see it. This is the beating phenomenon that I was talking about from before. I'm not touching anything. This is just two frequencies playing at the same time that are very close, but slightly different. And notice how frequently the pulse is coming up. About every half of a second, every 0.6 of a second, the difference between those two frequencies. Now let's bring it up somewhere that you can maybe hear it a little bit better. Now this is 164.8 and 166. So a beating of 1.2. And we can see it there, going back and forth. Ramp it up again if we'd like. And that's like a difference of one octave, and they're slightly off, and that's why you're seeing them kind of dance around in a very similar pattern. But you can hear a wah effect coming out of these. And if you take these frequencies and you start to raise them, now this difference is much more substantial. There is a third pitch being generated here. And actually, let me see if I can get this exactly. So let me set that at 330. Let me set this at 440. There is my extra E sound coming in. Or actually, no, it's my A sound in this case. Two frequencies generate a third simply because of the interference between the two of them. If I play that A, you can see where that peak actually lines up. But it's included in there. It's part of the beating between these two. At this point, though, the beating is much more substantial. It's no longer hearing a pulse in the sound, but it's showing up as a frequency to our ear. Now, all of these other sounds that you have heard from before, right? There's all sorts of different things going on here. It's not just something like a sine wave. I have said everything is sine waves, but sine waves alone are not what's used. Superpositions of many, many, many sine waves are actually used. So let me go back to this picture real fast. If you can see, I've got a handful of different types of waves here. I've got square waves and triangle waves and sawtooth waves. Triangle wave, for one, you can see it. Now it's a lot more spiky, but notice it sounds a little bit more rigid because triangle waves are made up of a bunch of different odd harmonics. If I take a sine wave and a lot of its odd harmonics and I add them all up together, I get something like a triangle wave. It's the interference of many different sine waves to get a sound like this. A square wave, sawtooth, back to our pure sine. Each of these, you start to hear more and more of those higher frequencies, the overtones, that give them that unique sound. So, hopefully, has the sound been kind of running through? Have you guys been able to kind of hear it when I change some of these sounds at the very least? I know a lot of these things like to do noise cancellation on a lot of these frequencies. So, hopefully it's at least kind of coming through this, but this is all the cool stuff going on with these. I love to see a lot of these different factors, a lot of these different things playing into it. I think it's tons of fun to mess around with. And all of this stuff, this is not anything that I learned in one specific course or learned from one specific person. In fact, the first time that I was inspired to do something like this, it was because my guitar teacher also had a physics degree before he got into music. And he likes to run this Science of Music show. And I heard about this for the first time, and I thought, well, that's fascinating. That sounds like tons of fun. And I've kind of made my own setup for this thing. All of these are details that I'm positive I would fail a class if somebody saw a wiring like that, right? That's not a good wiring by any means. But my experience, knowing what's going on, being able to apply this stuff, this is where it's a lot of fun. This is why I do like the Friday questions and things like that. You've got a summer coming up here. Spend some of that summer doing cool projects like this, things that interest you. It doesn't have to be an oscilloscope with a guitar. Although, with how I know the engineering school is, everybody plays guitar. But find some cool things going on there. Get some hands-on experience with some of these things. Don't be afraid to mess some stuff up a little bit. It's not a big deal if it messes up. If I fry a wire here or something like that, it's not the end of the world. Go out there and explore some of these things. Have some fun with it. Now, I do have all of this stuff set up, and that, I think, is all the stuff that I had planned for a demo. But if there's anything that you want to see while I've got all of this equipment hooked up already, I'm not doing this again. It's too much of a hassle. I've got wires. You can see kind of the wire going back there. That connects the pedal board to the amp, and the other wire is hanging over here, drops into that. I have everything wired up in the most disgusting way possible, and I'm never doing this again this semester. If I'm teaching this course again, then I'll run this experiment again and show all this stuff off, but it's too much hassle to do frequently. If there's anything you'd like to see or any questions you have about this stuff while I've got it all out, I am more than happy to answer anything or try some of these things out. Just let me know. But otherwise, thanks for being here, team. Go forth, work on all this stuff, keep being successful, doing all the great things that you're doing, and have a great weekend. I'll see you next time around.